Hey, welcome to topic 4 in our electricity unit on looking at energy efficiency. When we talk about energy efficiency, we need to be familiar with the different types of energy that are available because energy efficiency compares the output energy to the amount that we have to put in to the device to get it going. And so let me show you the slide that talks about different input and output energies. So here are some common forms of energy that might either be the input or output of a device. Some devices and machines have what's called chemical energy, which is energy stored in chemicals, and it's released when the chemicals react. For example, food has chemical energy, and fuel have chemical energy. Electrical energy, we know, has to do with moving electrons. Mechanical energy deals with the motion of things. For example, a windmill has mechanical energy. Basically, any mechanical device that has moving parts to it. And a fourth common type of energy we see is thermal energy. That's energy associated with heat. When we speak of analyzing different devices or machines, we need to be aware of what their input and then intended output is. So let's look at some devices. A toaster, for example, the one that we plug into the wall, its input would be electrical, and its intended output, that is to say, what's its purpose, and that's to cook things. So the output would be thermal. Don't get me wrong, toasters have other forms of output energy, but they're unintended. For example, if you shut the lights off and you turn your toaster on, the toaster does give off a little bit of light energy. Flashlight, a battery-powered one. Its input is chemical because of the batteries. Its output is, of course, electrical and then light. However, light would be the intended output. Whenever light is given off, of course, an unintended output is heat or thermal. How about a blender? A blender input, electrical. Output, because of the moving parts, mechanical. Sound might be an unintended output. Sound energy might be an unintended output. A battery-operated clock. Batteries are chemical. Output, well, the intended output would be mechanical because of the moving hands. However, sound is another output. Light might be another output as well. Here's a device that I wanted to talk about that's in our textbook. It's called a thermocouple. It's a neat little mechanical device because it converts thermal energy into electrical, and then it converts that into a temperature reading. So these devices are used in ovens, for example. They're specialty thermometers, and a thermocouple operates under that energy conversion. Let's see if we can pinpoint the input and output energies of these devices. So this is a handheld barbecue lighter. What would the input energy be for this? Well, it would be, if you said mechanical, you're right. We use our hand and we move our trigger finger to cause a spark. And what's the output? The output for this one is chemical. The intended output is chemical to thermal. So from chemical we go to thermal. Now it has an unintended output, and that might be light. but we use the thermal energy to light matches and so on. Let's look at the solar powered house. What's the input? The input energy for this one is light energy from the sun. And the output is, it converts it to electricity, solar powered electricity, which then can run different things. So output is electricity. This is a boat operated by a candle. So the input would be thermal because the heat from the candle boils some water in here. So thermal is the input. The output will be mechanical. So input is thermal for this boat, and the output is mechanical because it's moving. Battery or solar powered flashlight, I think that's a solar cell. So the input is light and the output would be light. Weird, hey? So it goes from light to chemical energy to electrical, then to output light. We can actually calculate the efficiency of machines by comparing the output divided by the input and then timesing it by 100 to get it into a percent. Let's look at some light bulbs and we can calculate their efficiency. This is incandescent and this is fluorescent. If the amount of input, which is electricity, to run the light bulb is 1,000 joules of energy, and the output is 50 joules, what's its efficiency? Well, 50 joules divided by 1,000 and then times by 100 to get it into a percentage. So 5% is what you would get for this type of light bulb. It's only 5% efficient. So the rest is wasted energy, 95% wasted energy in the form of what? Well, they get pretty hot. So most of the wasted energy is in the form of heat or thermal energy. This one, let's look at it. So what's the output? 100 joules, so it gives off a little bit more light. 100 joules is the output. The input doesn't take as much energy, 400. So divide by 400 and times by 100 to get it into a percent. And 100 divided by 400 is 1 over 4. That's 0.25 times 100 is 25% efficient. A little bit better. These light bulbs are really efficient. They're called LEDs, or light emitting diodes. And the principle behind them goes something like this. As particles come through a gap, which is right here, they're excited and their electrons are sent upward through this tiny little gap, and the electrons, when they jump up an energy level, can give off a little bit of light. And so if you've ever touched these, they're not very hot. They don't get very hot. They're only 7% wasted energy. The rest goes towards light, 7% waste. Here's some more devices and their efficiency ratings. So we looked at that one already. Internal combustion engine, which is in most vehicles, is about 10%, fluorescent 22 to 25. A hydrogen fuel cell, 60%. A turbine, steam turbine, 45. And our human body, not that efficient, only about 25, because as you know, we start to heat up as we exercise. So the food we eat is the input, output mechanical, okay? But we heat up, and a lot of that efficiency is in the form of heat. These are electric cars, and they're pretty efficient, and we'll watch a documentary called Who Killed the Electric Car. I want to talk about enter guide labels. In Canada, you can, when you buy new appliances, you can get a sticker on it that tells you a bunch of things about the device. So it tells you how much electricity it uses per year, kilowatt hours, and then it tells you if you bought this fridge, it would sit somewhere here on a scale of devices, and here is the most inefficient model, which means it uses the most electricity, and here's the most efficient model, okay, which means the device you're buying, whether it's a fridge, is right here on the scale or spectrum, so almost one of the more efficient types of devices or models, which is pretty good. The drawback is obviously you probably pay more money for a more efficient device. No machine is 100% efficient, okay? That's impossible on Earth. Some is always transferred into wasted energy in the form of heat. And that's my quick introduction to energy.